Hi everyone, welcome to video 3.1. This is your first video in our third unit, which is all about energy and thermodynamics. And you'll learn what that word thermodynamics means in this video. So this video is just meant to be a synthesis of some of the main ideas and vocabulary words that you saw in the first 4 lessons of the textbook. So to begin, I want to answer the question, what is energy? So this unit is all about energy in chemical reactions and chemistry, so we need to talk about what energy is. And it's not so simple. Energy is actually a pretty difficult concept to wrap your mind around. It's not like molecules or atoms, which I can draw you a picture or a model of. It's not a substance, you can't touch it. Energy is, we say it's a measurement of how much something can change or move. So there are different ways that a substance can have energy. Temperature is a way that something can have energy. Light, chemical bonds have energy, and something in motion has energy. So having a lot of energy can also mean that you have the ability to change something's temperature, the ability to create light, or the ability to break chemical bonds or to cause motion in an object. So in this particular chapter, we're not looking at motion so much, but we're looking at temperature and changes in energy that come from changes in temperature. And we're going to look a lot at chemical bonds, because when we talk about chemical reactions, we're talking about chemical bonds, which takes me right to my next question, which is, how is energy connected to chemistry? Because you could talk about energy in a biology class, in a physics class, in an earth science class. We talk about it in chemistry because it's related to chemical reactions. So you should remember from our last unit that a chemical reaction is when you change matter, you change molecules. So you either are breaking bonds between atoms, making new bonds, or a lot of times both. So for example, in this chemical reaction, I'm mixing 2 molecules of H2 with 1 molecule of O2 to create 2 molecules of H2O. So to do that, I need to break this chemical bond, break this chemical bond, break this chemical bond, and then make new bonds to create the water. Breaking these bonds requires energy, and making these new chemical bonds will release energy. So anytime we have a chemical reaction or a change in matter, we're going to see changes in energy. And that's what this whole chapter is about. So, as I mentioned before, this unit is referred to as thermodynamics, which sounds like a big complicated word, but it doesn't need to be. You can break it down. So the prefix thermo has to do with heat, or if you think thermometer, temperature. And the word dynamic means change. And so when we're talking about thermodynamics, we're talking about changes in temperature and changes in heat. And that's what this unit is. So there are what we call the laws of thermodynamics, which are just rules that we see when we talk about changes in heat. So the first law of thermodynamics is that energy is conserved. So often we think about something's energy being used up. That's a very misleading sentence. Energy doesn't get used up. It just gets transformed. So when we say energy is conserved, what that means is that it never disappears. It only gets transformed from one type of energy to another. So for example, if I let a pot of hot water cool down, the energy isn't going away. It's just being transferred into the air. The second law of thermodynamics is that energy tends to disperse. And we see that with heat. Heat tends to disperse. If you think about sitting by a campfire, the heat is going to spread out. So we've talked about what energy is. We've talked about how it's connected to chemistry. So the next question I want to address is, are heat, thermal energy, and temperature the same thing? And the answer, you can probably predict if I'm asking this question, is no. And so it's important that I explain to you the difference between these three vocabulary words, because in everyday language, we use them to kind of mean the same thing, but they're not the same thing. So in chemistry, I'm going to expect that you know how to use these three words and use them correctly. So I'm going to start with temperature. Temperature is a measure of the average kinetic energy of molecules in a system. Kinetic means motion. So when I'm talking about kinetic energy, I'm talking about how fast the molecules are moving. So if I have here a molecule of, let's say, water. Here's my oxygen. Here are my two hydrogens. The temperature is related to how fast the molecules in my water are moving around. They're always moving. They're bouncing all over the place. How fast they're moving, on average, is temperature. So what we feel against our skin is either a hot temperature or a cold temperature is really just a measurement of how fast the molecules of whatever we're touching are banging into our skin. Temperature is just fast-moving molecules. And I use the word average because it doesn't matter how big or small the object is or how much I have of it. It just has to do with how fast the molecules overall are moving. So for example, if I have a really large brick or a really tiny brick, if the molecules inside are moving at the same speed, they feel the same. How much of the brick I have doesn't matter. That's not true for thermal energy. Thermal energy is how much total kinetic energy the object has. And so thermal energy does depend on temperature, because it has to do with how much total sort of movement the molecules have, but it also depends on amount. So for example, if I had a tall glass of water and a short glass of water, and they were both the same temperature, the tall one would have more thermal energy because it's got more total molecule motion, because even if the molecules are moving at the same speed in both glasses, the taller glass has more molecules. So there's more total thermal energy. So temperature, how fast are the molecules moving? Thermal energy, how much total molecule motion is there? So it depends on temperature and amount. Heat is actually the transfer of thermal energy. So when we're talking about heat, what we're talking about is thermal energy moving from one substance to another. So an example of heat, let's say I take a bunch of ice cubes out of the freezer and I just put them on a plate and let them melt. Well, the reason they're melting is that thermal energy is moving from the air to the ice cubes. So the ice cubes are absorbing thermal energy from the air. So we call that heat. Right? So there is heat coming from the air to the ice cubes. Now, speaking of temperature, I need to briefly mention how we measure it. I'm going to talk later about how we measure thermal energy and heat, but temperature we need to talk about because there are different systems for measuring temperature. So, oops. All right, there we go. So you're probably familiar with the with the Fahrenheit. All right, so you're probably familiar with Fahrenheit as a system for measuring temperature, we're actually going to use Celsius. It's a more scientific measurement. So the degrees Celsius is based on water. 100 degrees Celsius is the temperature where water boils. 0 degrees Celsius is the temperature where water freezes. There is also a temperature system called Kelvin, but we're not going to talk about it in this course. We're really just going to talk about degrees Celsius. Okay, how does heat flow during a chemical reaction? So in order to talk about heat flow during a chemical reaction, we need to talk first about two really important vocabulary words: system and surroundings. The system is what we're focusing on. It's whatever our chemical reaction is, or whatever we're looking at as the focus of our measurements is our system. Everything else is called the surroundings. The thermometer, the beaker, the air, the table, anything in contact with the system is the surroundings. So there are two types of chemical reactions, and you've seen this before. One is endothermic, and the other is exothermic. In both types of reactions, we've got the transfer of energy, right? Energy is either coming in or going out. Endothermic, means heat is entering. And so if heat's entering, it's coming from the surroundings into the system. Conversely, in an exothermic reaction, heat is exiting. That's what the prefix exo means. And so it's going from the system to the surroundings. So let's take a look at how this would pan out in a reaction. So this first reaction is endothermic. Endo, heat enters. So we've got thermal energy moving from the surroundings to the system. The system is where the chemical reaction is happening, and it's absorbing thermal energy from the surroundings. Now, that also means it's absorbing thermal energy from the thermometer, because the thermometer is part of the surroundings. And so if it's absorbing thermal energy from the thermometer is seeing a decrease in thermal energy. It means the molecules in the thermometer are going to start to slow down, and the temperature will decrease. So in an endothermic reaction, we see the temperature go down because it's pulling heat away from the thermometer. Similarly, if I were to put my hands on the side of this reaction flask, it would feel cold. And it would feel cold because if it's endothermic, that means it's pulling the heat away from my hands. Heat is going to be leaving my hands so that it can enter the reaction. So this would feel cold. Exothermic is going to be the opposite on all fronts. Heat is exiting the reaction. It's leaving the system into the surroundings. The thermometer is included in the surroundings. And so we have heat transfer from the system to the surroundings, means thermal energy is going into the thermometer. The kinetic energy of the molecules inside the thermometer goes up, they speed up, which means we see an increase in temperature. And again, if we were to put our hands on either side of this flask, it would feel hot. And it would feel hot because we've got kinetic energy leaving the reaction going into our hands.